Hello, welcome to the Q-Munity Tutor TipVid on Section 7 Quantum Teleportation. Now, if quantum teleportation doesn't get you excited, nothing will. It really is the epitome of everything quantum. I just would like to say that the Chinese in 2016 teleported a photon, which is an empirical unit of light. They teleported it from a laboratory in Tibet to an orbiting spacecraft, the Messias. And this is the stuff that Star Trek's made of. It's wonderful. But let's get into it a bit. I just want to talk about what it is. And I want to talk about it conceptually. So I think if we work out the process rather than discussing the whole teleportation in its entirety, I think that really is helpful, right? So we are teleporting quantum information. We are teleporting a quantum state. Now, when I talk about quantum teleportation to my students, they nearly always ask, good question, by the way, but they nearly always ask, how do we know that the particle that's being teleported is the same as the original one? And it's a very good question. And we know it because the quantum state is the same. And incidentally, the particle will instantly be at point B, and it won't be at point A anymore. It collapses during the process. I want to tell you what quantum teleportation isn't. It's got nothing to do with wormholes, loopholes, and space-time. It's nothing to do with disassembling the atom and then reassembling it. It's not that. And it's not scanning the object and sending the instructions to reassemble at another place. It is this using this strange quantum entanglement to be able to send the actual quantum information. Now, it's really important to understand the process. So what I'm going to do is explain that to you. And I'm going to forget about the distance. I'm going to pretend that the two qubits are next to each other because the process is exactly the same. So let me explain it. Okay, so let's see exactly how it would work if it was in the one laboratory. So we're not talking about distance, we're just talking about transferring quantum information. So what do we want? We want Alice's qubit, which is psi, and that equals alpha ket 0 plus beta ket 1. And we want that to go across to Bob. And we will have, so that's Alice's qubit. And we will have Bob's qubit, which will be initialized to 0. And then there's going to be a NOT gate, because that's how you actually create a Bell state. And I'll explain that in a second. And this gets us to the Bell state, one of the Bell states. There's 4 main Bell states which are maximally entangled. But it's alpha 0, 0, ket plus beta 1, 1, ket 1, 1. And that just means that we have a state whereby both of those qubits are entangled as one. But what do we actually want to do? And what we actually want to do is get psi to go over here to Bob's state. So we want to collapse Bob. We want to collapse that to psi, so that it's exactly what we want. And we can do this through entanglement. That's the beauty of the process. So when you've got a Bell state, we can influence one qubit with the other. Let me explain more. Okay, well, what we actually want to do is get the Bell state collapsed into psi at Bob's end. So what can Alice do? Now, Alice could measure in the computational basis, which is 1 or 0, but trust me, that won't work out. She has to measure in the plus or minus basis. Okay, so let's look at Alice's state. So that's the product of this side. This is called the product state, and it's a tensor product between Alice and Bob's qubits. So you just multiply them together. So just making sure you realize psi is alpha ket 0 plus beta ket 1 equals that psi there. And then we have to multiply that by ket 0, which is that ket 0 there. So the product state equals alpha ket 0, and multiplying that ket by that ket. So here we apply the CNOT gate to the product state, and what that does is flips Bob's second qubit to 1. So the product state at the end of the CNOT operation is alpha 0, 0 ket plus beta 1, 1 ket. Okay, so as we say, Alice can measure her qubits in the plus or minus basis, sometimes called the Hadamard basis or the Sine basis. It's different from it's just a rotation from the computational basis, which is 0 and 1. So all you've got to remember is that a 0 in the computational basis equals the square root of 1 over 2 ket plus. So if we measure it, then what we'll do now is substitute the first qubit, and we will substitute that for 1 over square root 2 plus. So we will have this all equals alpha 1 over square root 2 plus 1 over square root 2 minus, and all of that tensor product times ket 0. And we'll do the same for the other side of the product state. So we will put in a 1 here, and the 1 equals 1 over square root 2 ket plus minus 1 over square root 2 ket minus. So all that happens, if it's a 0, it's a plus, and if it's a 1, it turns into a minus. So we've now got all of that plus. So I'm now doing the second computation, which is beta 1 over square root 2 plus minus 1 over square root 2 ket minus, all times tensor product ket 1. So it's beginning to make a little bit of sense now. All we're doing is getting the product states, we're multiplying them all out, and we're just measuring it on the sine basis. That's all we're doing different. So the first qubit, which is Alice's qubit, we're measuring on the sine basis. We're not measuring Bob's qubit on the sine basis. So now here what we can do is we can take out, so all I'm now doing is using this large equation here, and I'm taking out the square root 1 over the square root 2 plus, so I'm taking that out, and that leaves me with alpha ket 0 plus beta ket 1. And that's going to be, so that there relates to that sentence. And the second one is here, 1 over square root 2 on the minus ket. And that leaves us with alpha ket 0 minus beta ket 1. Okay, well, we're getting a little bit closer to actually what we want. Okay, so it's all we've done is we've worked out the product states, and then Alice has measured her qubit in the sine basis, and then we're looking at the product state now after she's measured her qubit. Now, if she gets a 0, then it will, this is what she gets if she gets a 0. She's getting 1 over square root 2 plus, and then alpha ket 0 plus beta ket 1. And this is exactly what we want. This is psi. So if, and see, this here equals 0, as we spoke before, in the sine basis. So if she gets a 0, then that cancels out this 0, and all you've got left is psi. So it's exactly what we want. Now, if she throws a 1, then it equals this bit up here in the top right. And all it leaves us with is alpha ket 0 minus beta ket 1. Remember that, because measuring 1 on the sine basis, you know, is an equivalent of 1 over square root 2 minus alpha ket 0 minus beta ket 1. So all, if she gets a 1, all Bob has to do is put in a Z gate to change the phase, and that will change this minus to a plus, and that equals psi. So really all that happens is they get a belt state, Alice measures her qubit in the sine basis, and then she measures the qubit. If she gets a 0, Bob does nothing. If she gets a 1, Bob applies a Z gate. And that really is all there is to it. Thank you very much. I hope this has helped you in some way, and I'll see you in the next section. Thank you.